In the world of functional programming, Haskell is often treated as a language of pure theory. It is the subject of academic papers, the playground of mathematicians, and the benchmark for type system complexity. The prevailing narrative suggests that such a rigorous approach belongs in a university lecture hall, not in the high-pressure environment of real-world financial infrastructure. But there is a story that challenges this assumption, a story about a company called Mercury that built a production system with millions of lines of Haskell code. This is not a tale of academic purity winning over practical reality. It is a story of specific, painful failures and the hard architectural trade-offs required to make a million-line codebase work when the lights are on and the money is moving. Most talks about Mercury's success focus on the victories. They highlight how the strong static type system acts as a comprehensive documentation tool that reduces cognitive load. They praise the engineering culture that prioritizes rigorous code review and type-driven design. These points are true, but they tell you what the architecture looks like on a good day. They do not tell you what happens when the compiler is right, but the business logic is wrong, or when the very features that make Haskell safe become the bottlenecks that slow down development. To understand the reality of running a multi-million-line codebase, we must look past the polished presentations and examine the friction points that official talks often omit. Consider the sheer scale of a 2 million-line codebase. In a traditional object-oriented language, you might expect a sprawling web of dependencies where a change in one class ripples unpredictably through the system. Haskell offers a different promise. It suggests that if you get the types right, the compiler guarantees that your program will not crash due to null pointer exceptions or type mismatches. This sounds like a dream for maintainability. However, in practice, the cost of this safety is a unique form of technical debt. When you write in Haskell, you are constantly negotiating with the type checker. The compiler becomes a gatekeeper that demands absolute precision. Quick resource note before we go deeper. I keep a curated set of Amazon search links in the description for the kinds of desk gear, local AI hardware, storage, power, lighting, and builder tools that are perfect for engineers and builders like us. Some are affiliate links, so I may earn a commission at no extra cost to you. Please help support the channel. Use these links as a starting point if you're upgrading your own setup. Here is the thing that production engineers discover only after years of work. The type system is not just a safety net, it is a constant source of friction. When you try to refactor a core module, the type checker does not just tell you what is broken. It forces you to rethink the entire data model. This can feel like fighting the language itself. You might spend days refactoring a function not because the logic was wrong, but because the type signature was too rigid to support the new requirement. The compiler is correct, but the business need has evolved in a way the existing types cannot easily express. This leads to a critical trade-off that is rarely discussed in academic settings. To maintain velocity in a massive codebase, the team at Mercury had to develop strategies that prioritize pragmatism over purity. They learned that sometimes the most type-safe solution is the one that is hardest to implement, and the most pragmatic solution is the one that introduces a small amount of risk. They had to decide when to relax type constraints and when to enforce them with religious fervor. This is not a binary choice. It is a continuous negotiation that happens in every code review. One specific failure mode that emerged involved the interaction between the type system and the runtime performance. In Haskell, the lazy evaluation model is a powerful feature. It allows you to define infinite data structures and only compute what you need. But in a production financial system, predictability is paramount. The team found that the garbage collector, which manages memory automatically, could behave unpredictably under heavy load. The very laziness that made the code elegant caused spikes in latency that were unacceptable for high-frequency trading. To solve this, they had to introduce strictness annotations. These are explicit instructions to the compiler to evaluate expressions immediately rather than lazily. But adding these annotations is not a simple task. It requires a deep understanding of how the runtime scheduler works. Every time they added a strictness annotation, they had to measure the impact on memory usage and CPU cycles. Sometimes, a small change in how data was structured would cause a massive increase in memory allocation, leading to system-wide slowdowns. This is a side of production engineering that the type system does not protect you from. The compiler can guarantee that your types match, but it cannot guarantee that your program will run fast enough to matter. The engineering culture at Mercury evolved to handle these challenges. They prioritized rigorous code review not just for correctness, but for understanding the trade-offs. When a developer proposed a new type-safe abstraction, the review process did not just check the syntax. It asked how this abstraction would impact the garbage collector. It asked how it would affect the latency of critical paths. It asked if the performance cost was worth the safety gain. This level of scrutiny is what allows them to maintain a codebase of this magnitude. The success of deploying a million-line Haskell codebase demonstrates that functional programming languages are viable for large-scale financial infrastructure. It challenges the perception of Haskell as merely an academic or niche language. But this success was not achieved by following the rules of academic purity. It was achieved by bending those rules to fit the realities of production. The team learned that the type system is a tool, not a master. It is a powerful ally, but it requires a human to guide it, to understand its limitations, and to make the hard calls when the perfect solution is not the practical one. The journey from academic theory to production reality is paved with specific failures that no tutorial can predict. It is about learning how to live with the compiler, how to balance safety with speed, and how to build a culture that values deep understanding over quick fixes. The story of Mercury is not just about the code they wrote. It is about the decisions they made when the code would not cooperate. It is a testament to the idea that even the most rigorous type system cannot replace the judgment of experienced engineers who know when to push back against the language and when to embrace its constraints. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.